Okay, so we already derived fluid equations starting from the very basic Maxwellian distributions. We derived ideal fluid equations. Then also we saw that how the different type of forces can be retrieved using macroscopic approach, and in the same way actually continuity equations can also be derived macroscopically, that you can see any standard book of fluid mechanics. Uh, Now after that we also discussed several properties of ideal fluid equations. Now we will discuss a very interesting thing of interesting thing in fluid dynamics, so which is the the theory or the discussion of the invariants. Okay, and then another, the associated concept which we'll discuss will be the conservative form. So as you can always appreciate that we are physicists, so basically always, like a true physicist, we can be interested in knowing that whenever we can write the equations of, for example, ideal fluids, let's say this set of equations, for example, okay, these three, the continuity equation, the momentum evolution equation, and the internal energy evolution equation, then of course the question is that whether there is something which are constants of motion or not. Okay, and for that we basically try to introduce this for conservative form. Okay, so we know that in particle dynamics, when we talk about Newtonian mechanics or Hamiltonian mechanics, A is a constant of motion if d dt of A is equal to 0, right? For example, energy. Okay, if the total energy of a particle in a conservative force field is constant, then d dt of the sum of its kinetic energy and potential energy is 0. Okay, now in fluid this thing is still valid, but now try to understand one thing. This thing should be valid for a fluid particle. So always we will remember that whenever we need to like draw some analogy with some the particle mechanics or particle dynamics, okay, to fluid, the best way is to talk to replace a Newtonian particle, okay, a traditional particle, by a fluid particle. Then only we can write the Newton's second law for that particle, fluid particle. Okay, so here you can see that if we just say that this ddt is nothing but the Lagrangian or the material derivative, okay, then if A is, also in fluid mechanics we can say that A is conserved if d dt of A is 0, and if you just expand d dt, you know that you will have del t plus u dot nabla. Okay, it's not u dot nabla, sorry, it is v dot nabla, where v is the bulk velocity. Okay, yeah, bulk velocity of the fluid. So v dot nabla, and then this equation, which is exactly equivalent of writing ddt of A is equal to 0. So, and then this ddt is equivalent to del t plus v dot nabla, this. Okay, so this is true also for fluids. So just once again, don't get confused. For fluid nothing actually changes, but then we have to understand one simple thing, that finally we have to write everything in terms of Eulerian things, and in fluid actually, okay, we have subtle things to add. Actually, we have additional considerations which we should not forget. Okay, so if you simply now see this, just a minute, if you just see this, this formula, as I just said here, this formula can readily be applied when A is an intensive variable. Okay. For example, now for fluids, of course, there are subtleties. When we are talking about a simple particle, well, there is nothing called intensive or extensive. Okay. But when we are talking about a system, broader system, okay, having some volume, okay, then we have, you know, maybe from thermodynamics that we have two types of variables. One is called extensive variable, another is called intensive variable. Intensive variables are such that they are actually, I mean, for a system, for a system. So if let's say the temperature, so if you have a container of gas, so intensive properties are such that they are, if the system, if the total container is now divided into n number of subparts, then of course imaginarily divided, then for every subpart the value of the intensive variable is just that simple, I mean simple variable. That means let's say if your system is, let's say if your gas is at rest and there is a there is a uniform temperature throughout the body, so your system is in thermal equilibrium, or if the system is in dynamical equilibrium or mechanical equilibrium, the whole throughout the whole system you will have one pressure. Then at that point, if you just imaginarily divide the whole system, okay, then for every subpart the value of the pressure and temperature is the same. On the other hand, if you just take the mass, for example, then if you divide the whole system in imaginary subparts, the mass of the subparts will be, different. And when you add up the mass of the subparts, then you will finally get the total mass of the system. So something which, when, in a thermodynamic or static system, okay, when there is, how to say that, when there is an equilibrium of some type. So for example, some macroscopic quantities like temperature, pressure, they are uniform throughout the bulk. Okay, so this type of and this type of thing will have the same value even for any sub volume. Okay, any sub volume, when it is divided in some n number of sub volumes imaginarily, then this property is called an intensive variable. This variable is called. Now when the system is in flow and not in equilibrium, for example in a fluid, so at every point it has some pressure, it has some temperature, okay, but once again, then this is true that when you imaginarily divide the system, when you just imaginarily divide the system in n subparts, then it is true that the at every subpart the value of the temperature and pressure, they are not the same. But then in that case also you can talk about intensive variables. If you just see that uh, when they will have some value, but the total value of the temperature, okay, the total value of the temperature, or the representative value of the temperature of the fluid, okay, does not have any physical meaning, okay, when this is added over the number of subvolume. That means if you for example, if you now take a fluid or a flow field, something is flowing, and you divide the whole system into n subparts, then you calculate the temperature for in all the in subparts. Now if you add the all temperatures, So the if does this sum represent the total, I mean the actual temperature of the system? Of course not. That doesn't have any meaning. On the other hand, and the same thing for pressure, on the other hand, if you are talking about number density, then actually this will be added to give you the total number density of the particles inside this volume, right? So this is something you have to be careful that not number density, but I am saying that the mass, okay, not number density, because number density is intensive, because it is mass, it is number per unit volume. What I am just trying to say is the number itself. So just the number of particles inside every imaginary subparts, if you add them, they will give you the total number. Of course not the number density, sorry. Number density, pressure, temperature, they are just basically intensive variables, yes. But the total number, the mass, okay, the entropy, all these things, if you just subdivide imaginarily the total system, whether this is at rest or in flow, if you add the numbers of the, if you add the value of the subsections, they will not give you the value of the total section. Okay, so that is the if you add the thing, they will give you the value of the total system if they are extensive variable. Okay. Now coming back to our original discussion. So if we are talking about an intensive variable, let's say pressure, temperature, then this type of cases, if we say that the pressure or temperature, this is constant, then simply we can say that for example, if I say that pressure is constant, then ddt of P, Lagrangian derivative of P is equal to 0, and then you can say from that del P del T plus V dot nabla P is equal to 0. Okay. But for extensive variables, okay, so basically that means that if when we say that an intensive variable is constant, that means we are talking about the local values. But when we talk about the constancy of the extensive variable, then we actually talk about the total value of the extensive variable. Okay. Then we actually define a density. So if we just, let's say we talk about an extensive variable A, then we define a density rho A for that variable, okay, at every point of the flow field. Okay, and the total value will simply be the integration of rho A over the volume. Okay, now when we are saying that A is conserved, then that means integration over rho A d tau, that is conserved, because that is nothing but equal to A. Okay, and so just remember the mass. If A is the mass, then rho is simply the density. So integration rho d tau is nothing but the mass. Okay, so the only thing is that when you, so for an extensive variable, when we talk about the conservation or conservation of thing, or something is constant, okay, then we say this should be a constant in time. So ddt of this thing should vanish. Now it is true that this is already something which is integrated over space, so that does not have any explicit space dependence. Okay, and as it does not have any explicit space dependence, basically we can simply write that ddt of integration rho A d tau is equal to del t of integration rho A d tau, because this integration rho A d tau can only have time dependence. So ddt and del t for this is equivalent. Okay, then we can say A is conserved in an ideal fluid if del t of integration rho A d tau is equal to 0. Okay, so of course one possibility is that, so for that, of course, one possibility is that if this is 0, then this del del t will be commuting with d tau, because this is a space operator, space integration, and this is a explicit time dependence derivative, that means partial time derivative, so they will commute. Okay, so you will see that del del t will enter, and you will have this one should be equal to 0 if A is conserved. So there are two possibilities. One possibility is that del rho A del t is 0. That is true. So it simply says that if some quantity's density, some extensive variable's density is explicitly independent, then for that quantity, actually we can say that this is the corresponding. So if the density is explicitly time independent, then the corresponding quantity, which is nothing but the integration of that density over d tau, is a constant of motion. Okay, there is another possibility. That possibility is a bit more interesting. That is, if del rho A del t is equal to a divergence of a vector w, then del rho A del t, okay, is equal to divergence of w, and then integration over del rho A del t d tau is nothing but integration over divergence of w d tau. And you can simply remember this type of term should appear in Gauss's divergence theorem, which should be then equal to closed surface integral of w dot in ds, where the integral is done on a closed surface which encloses the volume tau. Okay, so then actually you can see that we can always choose such a surface. Okay, we can take a the surface extending at infinity, so that at every point on the surface, either w itself vectorially or the w dot in vanishes, and finally we will have this equal to 0. So that is another way, and in the most frequent cases, this is the way by which we show the conservations in normal fluids. Okay, including ideal fluids. It is true that I said normal fluid, but normal fluid is not yet introduced. Just we are talking about ideal fluids now. Okay, so for an extensive variable to be conserved in a fluid flow, its density should satisfy the equation of type this. Okay, and this W will then be called the flux of A. So rho A is the density of A, and W will be the flux vector of A. Okay, so if you just remember the case of the continuity equation, you see that this is simply the mass density, and this is the divergence of another vector rho v. So rho v is called the mass flux. Okay, and this signifies the conservation of integration over rho d tau, which is the total mass. Okay, then what about the momentum equation? So that was a scalar equation. Now we have a vector equation, but the essence is the same. Del del t of rho v plus divergence of rho v vectorial v, okay, sorry, tensorial v, I'm sorry, is equal to minus divergence of p tensor plus rho times f. Okay, that is the external body force. Okay, and you can actually take this thing, to the other side and take everything inside this divergence. Okay, now if we say that if we don't have any external force, in the absence of any body force, okay, so in the absence of any body force, del del t of rho v is equal to minus of divergence of this thing. So then if rho v is the density of something, then this will be the corresponding flux. And what will be the corresponding conserved quantity is simply integration rho v d tau. And what is that? This is nothing but the total linear momentum. So you see, this is what? This is simply Newton's second law. Okay, that means in the absence of any net external force, the total linear momentum is conserved. Okay, now I have a very interesting and slightly twisting, slightly non-trivial exercise for you. That is, if we now consider, so that was just for compressible normal ideal fluid. Now if we are talking about ideal plus incompressible fluid, okay, then can you show that integration over v dot omega, where omega is nothing but curl of u, okay, so curl of v, curl of v, okay, so then can you show that v dot omega d tau integration over tau is a conserved quantity? Okay, so the same type of thing you have to actually show that the density, the evolution equation of the density, let me just use the true ink, del t of v dot omega, whether this should be written as a divergence of something or not. Okay, so that is something very interesting. You can try it at home. Okay, finally, the most important and the most intuitive one. So this is the conservation of energy. So a few steps of straightforward calculation, actually, just a minute. A few steps of straightforward algebra and calculation can give that del t of half rho v square plus rho epsilon. And what is this? This is the density of total energy, kinetic plus internal energy. Okay, this is equal to minus divergence of rho v times half v square plus omega. Okay, here omega has a different, I'm sorry for this, so this is not omega. I should have written something like this. I should have written something like h. Okay, so please you check what h is over here. Okay, so that is your task to do. So you try to find first if to evaluate this thing and to check whether this is equal to some divergence or not. If it is some divergence, then what will be h? Okay, so if you can show that, then basically you will be able to show the conservation of total energy. That is again the same thing. This calculation will be circulated later. Okay, but first this is your work to try it at home, because this is the most important thing. Okay, so this is because this is conservation of energy. If there is no conservation of energy, then there is some problem. Okay, so that is the most interesting thing, and that is a very good exercise. Okay, but I am giving you some hints somehow that so you have to calculate separately del t of rho epsilon and del t of half rho v square. So this is nothing but the sum of two terms. One is epsilon del rho del t, and this del rho del t can be obtained from continuity equation, plus you have rho del epsilon del t, and that is from energy equation, internal energy evolution equation. And then for the second one, you will have two terms. So there are so many possibilities actually. So one can write like this: del t of half rho v dot v. So then you can actually do it like del t of rho v dot v plus rho v dot del v del t. That is a possibility. What I personally prefer, that to just write it as rho times v square, okay, not rho vv type of thing, and then I write it like this: half v square del rho del t plus rho del v square del t. Then actually you just need only one form of the momentum equation, that is del v del t. Okay, otherwise you need del rho v del t and del v del t, these two. So that is somehow, that is also okay, but well, that's up to you to decide which one you will choose. You can do both. Okay, so if you do that correctly and carefully, you should be able to show the conservation of the total energy. We will come back to this problems of conservation again when we will discuss transport phenomena and real fluids, because then you will see that there are some type of effects. For example, you all know that some viscous effects will be coming there. So dissipation, so viscous effect is nothing but a source of dissipation. Okay, and then you will see that the energy conservation is only possible when the viscosity is negligibly small or zero, actually zero. Okay, so I mean, here we don't have all these problems. Here we are in an ideal situation. That's why energy is actually conserved. Okay, so you can, as a very interesting exercise, even for a compressible fluid, now you can actually check whether v dot omega is also conserved or not. Okay, so one was just for incompressible ideal fluid, another is for compressible ideal fluid. Now you can check that whether barotropic type of fluid closures can give you something additional or not. So all these things can be done actually. Okay, so I mean you can always think that again there are interesting things. For example, if your flow is now incompressible, and then your flow is ideal and two-dimensional, then which type of conservations are there? I mean, in the course of lecture, I can only tell you a very limited number of examples, but it is you to actually investigate more over internet, and then during the discussions you can also ask me questions. Okay, and so for example, for a 2D incompressible ideal flow, is there anything which is conserved like v dot omega? So actually we'll see there is something very, very interesting which is conserved there. Okay, so which is related to omega. Okay, so just try to find it out on your own. Okay, so I mean, that's all about for instance, that's all about the conservation principle of ideal fluids. So here basically we learned to write the equations in a conservative form. If that is true, then only we can think of the conservation of an extensive variable. For intensive variables, this is very easy and immediate. The form is immediate to write. Okay, thank you.